Pluto is a distant and mysterious dwarf planet, which was once a member of our solar system's planetary family. However, recent startling announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen, and what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon, or is 31 seconds. There's something more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was demoted to a dwarf planet partly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the red flag about a possible hazardous collision between these two. 1 minute and 3 seconds, planets, which could pose a huge threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even finished one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination. Angled. 1 minute and 37 seconds. At 17 degrees to the ecliptic plane, the path Pluto traces is much steeper compared to the other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the 2 minutes and 11 seconds gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep incline and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of space mechanics. The 2 minutes and 43 seconds three-body problem in space is about figuring out how three celestial objects, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all work together in a complex way. The terms azimuthal libration and latitude libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, what's keeping all 3 minutes and 15 seconds planets in their orbits is azimuthal libration. In the context of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from colliding. Latitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is situated significantly above their orbital plane, providing an 3 minutes and 48 seconds additional layer of protection from potential collisions. Another crucial component in this equation is the VZK oscillation. Named after three scientists, von Zeipel, Kozai, and Lidov, who studied how objects move in space, this oscillation describes how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This gravitational interaction affects their movement and contributes to the stability of Pluto's orbit. Even though Pluto's path seems unpredictable, the VZK oscillation helps maintain a form of order over long time scales. The 4 minutes and 22 seconds VZK oscillation shows that even if things in space seem wild and random, certain patterns and rules keep everything in order. All of these components help keep Pluto's orbit stable, ensuring that it doesn't crash into Neptune or get thrown off course. Understanding the three-body problem in this context helps us learn not just about Pluto, but also about our solar system and distant worlds beyond. Numerical simulations in the late 4 minutes and 53 seconds 1980s revealed that, despite these stabilizing properties, Pluto's orbit is technically chaotic. Minor deviations in initial conditions can lead to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping chaos at bay. Recent computer simulations have helped us understand how the major planets, Neptune, Jupiter, and Saturn, affect Pluto's path around the Sun. Neptune has a special resonance with Pluto, where 5 minutes and 24 seconds, 4 every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's path stable. But Neptune isn't the only planet playing a role. Jupiter's gravity also plays a crucial part in maintaining Pluto's orbit, and even Saturn contributes. These simulations show that Jupiter's gravity alone is strong enough to keep Pluto on a stable path for billions of years. Essentially, Neptune, Jupiter, and Saturn are all working together to ensure Pluto moves safely through space. 5 minutes and 58 seconds, without running into trouble. These orbital dynamics are essential for maintaining order and predictability in the movements of celestial bodies. Without such mechanisms, the solar system would be far more chaotic, with planets potentially colliding or being ejected from their orbits. For Pluto, understanding its orbit is crucial, especially with recent speculation about a possible collision with Neptune. This knowledge gives us a clearer picture of the solar system's dynamic nature. The case of Pluto demonstrates that even seemingly unstable orbits can achieve equilibrium through complex gravitational forces. It also underscores the importance of continuous observation, and the intricate gravitational dance between Pluto and Neptune is a testament to the delicate balance that governs our solar system. However, despite this stability, the question remains: could an external factor disrupt this harmony, leading to a future collision? Astrophysicists argue that while the current orbital mechanics prevent a direct impact, the long-term future of Pluto's path is not set in stone. From a passing asteroid, an undiscovered trans-Neptunian object, or even the gravitational tug of a distant star, could subtly shift Pluto's orbit over millions of years. 15 minutes and 18 seconds, such perturbations are not unheard of in cosmic history. Evidence suggests that in the early solar system, planetary migrations significantly reshaped orbital paths. The so-called Nice model, a widely accepted theory, suggests that Neptune itself once moved outward, scattering smaller objects and possibly even ejecting planets from the solar system. Could a similar event in the far future alter Pluto's fate? Recent studies suggest that an encounter with a large Kuiper belt object, KBO, could theoretically nudge Pluto's trajectory ever so slightly. While these effects would take millions of years to manifest in a measurable way, even the smallest change could accumulate over vast timescales, leading to unpredictable results. 15 minutes and 52 seconds. Another fascinating consideration is the hypothetical existence of Planet 9, a yet-to-be-confirmed massive planet lurking in the outer solar system. If real, its gravitational pull could exert subtle but significant effects on Pluto's long-term orbit. Some simulations suggest that Planet 9's influence could cause slow but steady shifts in the orbits of distant objects, including Pluto, over billions of years. While these scenarios remain speculative, they highlight the importance of continuous observation. Space is not static, and even the most stable systems can change under the right conditions. 16 minutes and 26 seconds. Despite these uncertainties, current models overwhelmingly support the idea that Pluto and Neptune will remain in their synchronized, stable dance for the foreseeable future. Their resonance acts as a cosmic safeguard, preventing catastrophic encounters. However, in the vast expanse of time, the smallest disturbances could compound, reminding us of the ever-evolving and unpredictable nature of the cosmos. As our technology advances, so too does our ability to predict these celestial motions with greater accuracy. New telescopes, deep space probes, and enhanced simulations will allow scientists to refine their models, providing a clearer picture of Pluto's fate. For now, Pluto remains a fascinating outlier, a relic of the solar system's chaotic past, and a reminder that the universe is far from predictable. Whether or not a collision with Neptune ever becomes a real threat, studying these orbital intricacies deepens our understanding of the forces shaping our cosmic neighborhood. 16 minutes and 59 seconds. As humanity continues to explore the mysteries of space, Pluto's story remains unfinished, a testament to the wonders of celestial mechanics and the boundless possibilities of the universe. Study. One of the most intriguing possibilities involves the influence of rogue planets, free-floating worlds that wander through interstellar space. If a rogue planet were to pass close enough to our solar system, its gravitational field could slightly disrupt the orbits of distant objects like Pluto. While the chances of this happening within a human timescale are incredibly slim, over millions or billions of years, such an event is not impossible. 0:18 and 2 seconds AM similar scenario played out in Earth's own distant past. Some astrophysicists believe that gravitational disturbances from an unknown planetary body may have caused the Late Heavy Bombardment, a period of intense asteroid impacts that shaped the surfaces of the Moon, Mercury, and Mars. If a comparable event were to take place in the Kuiper Belt, Pluto's orbit, though currently stable, could be subtly altered, leading to a slow but inevitable path toward Neptune. 18 minutes and 30 seconds beyond external threats, there is also the question of long-term solar evolution. Over billions of years, the Sun itself will change, expanding into a red giant before ultimately collapsing into a white dwarf. As the Sun loses mass during this transformation, the gravitational pull it exerts on all planets, including Pluto, will weaken. This could cause orbital drift among many solar system bodies, potentially altering Pluto's delicate resonance with Neptune. Some simulations suggest that in the distant future, long after humanity is gone, the shifting balance of gravitational forces could push Pluto into an even more eccentric orbit. While it is unlikely that this would result in a direct collision with Neptune, it could lead to closer encounters, increasing the chances of gravitational interactions that might further disrupt the Kuiper Belt. 19 minutes and 5 seconds The unpredictability of these cosmic forces serves as a humbling reminder of how fragile celestial mechanics can be over long timescales. While Pluto and Neptune remain safely locked in their gravitational dance for now, the future is not set in stone. The interplay of countless forces, both known and unknown, ensures that the solar system remains a place of perpetual motion and mystery. 19 minutes and 30 seconds As astronomers continue to refine their models, missions like the James Webb Space Telescope and future deep space probes will provide new insights into the distant reaches of our solar system. Perhaps one day, humanity will develop the technology to manipulate orbits, safeguarding planets and dwarf planets from cosmic threats. Until then, the story of Pluto, Neptune, and their intricate gravitational ballet remains one of the most fascinating enigmas in modern astronomy.